So, hi, this is yet another one of my talks about how Pythonistas think about software engineering. I've been doing talks in this direction for about 5 years now. And because I've been doing this for 5 years now, things are starting to get scarily abstract. Who saw my talk last year at KiwiPyCon? Yeah, so there's going to be fewer walls of code in this talk. I'm not going to be making Python do weird things today. I'm sorry, but thank you all for coming along and being awake to see my talk. So shall we begin? Here is a value of Python's. Simple is better than complex. And what better way to demonstrate how simple Python is than with the very first line of code that most people write in Python? Let's talk about print. Print is the first function that I see introduced in most introductory Python texts. Understanding print is really simple. You call it, you usually give it an argument, not like on this slide here, and some text gets displayed to the screen. This is fantastic. But what does print do under the hood? Here's the implementation of print. It's taken from the very source of CPython. The name of this function is not print, it's called built-in underscore print underscore impl. That's the name of the function that actually gets called. And if you judge by numbers of lines of code, which is how we judge how code works, you would say that what print does is error handling. And here's the line that actually takes an argument and writes it to what will usually be standard out. It is a call to a thing called pyfile underscore write object, which has its own whole world of implementation details to worry about. And what's most important about this is that this is all written in C. And as you've rightly observed, probably, this is a Python conference. And for Python people, understanding the C API is just going to add a whole bunch of undesirable complexity to this talk. But I'd like to take a moment to point out here, there is already complexity inherent in doing something very, very simple in Python. Rather than executing code that is written in Python, we're executing C code. Python needs to allow you to run C functions, and to keep that overall simplicity, it needs to present C functions to you, to the rest of the language runtime, no differently to how it presents Python functions. And the C API that's needed to facilitate that is itself quite complex. But this is a Python talk. I do not want to spend half an hour talking about C. So let's talk about Python. So print. To a Python developer, it has quite a complex interface. It's got complex behaviors that depend on how you specify those keyword arguments like file and flush. And that's complexity that I don't want to touch here. So let's narrow this scope even more. We're going to talk about printing just one thing, just a single argument. So we're going to define a variable, and then we're going to print the value of that variable. So let's set the value of our variable to a string such as hello world. So here is a really simple implementation of what print could do. We can iterate over each of the characters in the string, and we can write each character to a file sequence. Of course, it doesn't look like this under the hood. There's normally some complexity involving how block I/O works to make things faster if you transport longer strings in. But eventually there's going to be something going through all the characters in turn and putting them somewhere, most likely your terminal emulator. So there's already a bit of conceptual complexity here, but it's not too bad. But what happens if we want to print an integer? Well, that's not going to work because you can't iterate over an int object. So this code here, it won't work. So instead, we need to do some stringification. We need to stringify this parameter that we pass into print. And under the hood, that's going to do some fetching of method properties off a class that our parameter is a member of, and it's going to call that. And at this point, you can basically print anything if you know that pattern. But that stringify code is actually probably provided to us by the C library. So we're going to have to write our own if we want to make things as simple as possible. So we're going to write out our own stringify here. And that needs a bit of understanding of how ASCII works. You need to understand how to do base conversion of integers. It's a bit terrible. And that's before you even get to the implementation of this thing I didn't talk about, this put C thing, which is underpinned by a whole pile of sophisticated software and hardware concepts, which will eventually give you the text that you requested to be displayed on your screen. Which leads us to this. People don't set out to write complex code. There's two things that you should have learned from that discussion of print there. The first is that we should all want to interact with the simplest interface possible. Print is really, really simple to use. There is a lot of complex stuff underneath it. And the second is that even the simplest thing you can teach is going to hide a lot of that complexity. And I don't think that anyone would disagree that the best, most maintainable code you can write is the simplest code that you can write, under the constraints that we have to operate in whatever problem domain we're working in. Software exists because there is complexity in the world, and if we can model that complexity, then we can help people navigate that complexity. And by helping people navigate that complexity, if we do it right, things become simpler for them. And looking at print here is instructive. It only appears simple to us as Python developers because people have written building blocks, and with each tool, from the LCD elements in your projector there, all the way up to the Python interpreter itself, more complexity is modeled and simplified for us. Which leads me to some indisputable facts. The first is that complexity exists. The second fact is that it will be experienced by someone on a project. It could be an end user. It could be you as a programmer. And on a systems design level, complexity is either modeled or ignored. And more importantly, simplicity usually belies complexity on some level. Which is, put another way, anyone who is experiencing simplicity is doing so because complexity has been dealt with in some sort of way. Now, with that in mind, I used to think about how to build the simplest possible solution to a problem, which raises the question of what we might think is simple. I don't think this is a good question. I don't think it scales particularly well. Instead, if we accept that simplicity usually belies complexity somewhere within a system, then a better question is who within a system should experience simplicity? What parts of our system should be simple? And where should simplicity be experienced? And the main theme that I want to convey is that the answers to these questions in Python development are actually in flux. Python is an evolving ecosystem, and as new problems arise and new tools make different problem domains easier to navigate, our focus changes, and our focus will continue to change. Right. So the first idea I want to explore is this idea of internalized versus externalized complexity, which is one where Python has really changed its tune over the last few years. So who's heard of the batteries included standard library? Yeah, so all the old people in the room, basically, like me. There used to be this idea in Python that Python would come with everything that you needed to solve most problems out of the box. And this idea was really prevalent back around the time the Zen of Python was actually written. It's less relevant these days for a number of reasons that I'll get into, but that's not quite important right now. The other thing that's in the Zen of Python is this idea that there should be one and only one obvious way to do things. And I want to point out, like, this line was written as a joke at the expense of Perl, but there's still enough of us in this room and in this community who took it really seriously. But it was a joke, okay? So basically, if you took this idea seriously, you get this idea that Python will make the big decisions about how you would solve your problems, and everyone would have exactly the same Python as you, and you could read another user's Python code, and that would be nice. You could read everyone's code, and you could do the same thing with just the Python out of the box. So let's talk about urllib2. By the way, this 2 here, that's entirely down to Python not addressing the complexity of the standard library by supporting package namespaces back when Python was young. But I digress. These days, urllib2 is called urllib.request, and urllib2 was built around the idea that your code could be simpler if you could just drop URL handling code into Python code that uses existing interfaces. So it did this in what would be a really familiar way to a Python developer. Your request objects, they quack like files. There's an object-oriented interface for dealing with more complex use cases, and you had a way to install handlers for authentication and redirect handling without affecting global state. And in doing so, it let you do a reasonable job of modeling the complexity that arises from perfectly specified HTTP. But how does that look in practice? So urllib2 has authentication helpers. You can create a password manager to associate credentials with specific URLs. There is this HTTP password vomit up here. And then you can create an auth handler that supplies those login credentials. And then you create an opener that knows how to open URLs with those auth credentials. And you use that opener to open the URL. And then you treat the response like a file and you hand it into JSON.load. Easy, right? Really easy. This code becomes visibly simpler if you choose to not use features that are built into URL-lib2. If you deal with the complexity of authentication yourself, as long as you know how to write an HTTP authorization header, you can make a request with that header built in, and you don't have to write all that password manager crap. So you're forced to make a trade-off here. You either get simple code if you model your own complexity, or you have the complexity handled for you, but you spend a lot of time rigging up authentication handling. And the alternative nowadays is that you use a different library like requests. I tend to use requests or something with requests API. And the behavior around authentication is a lot more declarative. You say you want bearer auth, you make a request using those declarations, and as a bonus, you don't need to think about file handling. This is obviously much simpler code to interact with an authenticated HTTP API. You can make use of the library's work to model the complexity of authentication, and you get much shorter code. You don't need to make the same trade-offs. But why I'm talking about requests here is it's interesting because it chose to re-implement something in the standard library, and it chose to not be in the standard library itself. This was an odd choice at the time, but as evidenced by my question earlier, nobody knows what batteries included is anymore. It's mostly because of requests. This is just how things tend to get done these days. But by being out of the standard library, requests behavior could adapt as the broader web development community's attitudes changed, particularly around security. And it chose to model the complexity of interacting with HTTP services for end users. And as a result, the code that you need to interact with requests is much, much simpler. But is that gain in simplicity for you absolute? Oh, it's not, because now you need to model dependencies, and you need to model execution environments, and you need to think about keeping things up to date. So there is now added complexity in maintaining a project instead of having simplicity in your code, or while you get simplicity in your code. So which is the right choice here? Well, if you were making the choice to use requests or URL-lib2 in 2011, the choice might not have been immediately clear. And this was still fairly early in the trend of HTTP APIs, very much in the early adoption stage. Was it worth tracking dependencies so you could more easily hit APIs? Well, maybe if you interacted with a service like GitHub and you did that regularly with a lot of code, but probably not if you're like fetching packages off a Debian mirror or something like that, something that didn't need authentication. That answer has obviously changed with the way the web has changed over the last 12 or so years. So basically, you'd have a bit more first-party code whenever you needed to authenticate, but your overall code base would be smaller, and you wouldn't need to track external dependencies. The alternative is have less code, but more complexity in terms of the environment that you need to manage. And with retrospect, this idea of less first-party code is the approach that has won. And that's not because everything was in place 10 years ago. It's because we saw what requests did as a good way forward, and we built tools to help us manage the complexity that arose from deciding to manage external dependencies and configuration. We have very good tooling for configuration management like Git and things like GitHub. We have reasonable tooling for managing execution environments. We have a reliable and modern way to distribute those dependencies. And so now we're in a place where our definition of simplicity has actually changed. For an identical problem, a modern Python codebase will be much smaller than the one that we wrote 10 or 15 years ago to do the same thing, but the trade-off is that we increase the complexity of our configuration. We have more dependencies, but we also have more rigid environmental requirements. But those dependencies themselves, they model complexity for us. So we have configuration management tools like venv and pip to manage complexity. And for the modern Python developer, it seems like we get simplicity as a virtue of other people modeling a lot more of our complexity for us. And just a thought, if simple is better than complex, well, what does that say about the code that manages our environmental complexity for us? Is our code better than that code? Hey, so the second idea that I want to think about is one that is less conclusively answered in Python, which is the idea of how we go about managing complexity in a code base and whether the tools we have actually present us with simplicity. So specifically, I'm going to talk about quality assurance. The idea of quality assurance is the set of tools that we use to make our programs do what they're meant to do. But first, I'm going to talk about duck typing. Duck typing is this idea that two objects are interchangeable if you can use them in the same place and not get interface-related errors. If you're a type theorist, you would call this structural polymorphism. I'm not a type theorist, so I won't. Python's use of duck typing is actually a very simple type system, both to implement and understand. Firstly, there's no syntax in Python to describe types on an interface. You just have functions and variables, and this is simpler than Java or C++, which both require you to enumerate the types an interface expects. And on the other hand, there's no automatic coercion, so the language doesn't do complex behavior to make data behave in different contexts. This is simpler than Perl or PHP or JavaScript. Obviously, this puts some complexity onto you, but your code is slightly more reliable than Perl or PHP code would be. So here's some code that might not work. Have we absorbed that? Great, that might not work. So faced with some library code that might not work, you may ask yourself, well, how do we make sure our code is correct? And that normally comes down to two questions. The first is, what does your code do? And the other is, where should your code be used? And most of us, when we're thinking about how we make our Python code, how we harden our Python code, we normally think about this question here, what does it do? And you can solve this with tests. You test with numeric inputs, you test with strings, test with valid non-numeric inputs, combinations of all of the above. In short, we write tests. Automated tests help us manage the complexity of verifying behavior by allowing us to automatically run code that checks the code that we're verifying and make sure that works. And from a computer science point of view, what we're doing is describing a set of invariants. Invariance is a fancy term for a specification of some behavior that a system should hold, given a set of circumstances. So if an invariant stops holding, either the behavior is wrong or the specification is wrong, one of the two. And the more invariants you describe, the narrower the set of behaviors a system can hold. That is to say, invariants are a tool for managing complexity. And a unit test is a way to specify an invariant, which is the circumstances. Those are the data that you provide to the function under test, and the invariant is a set of assertions that are specified about the result. And this is really familiar to us as Python developers. It gives us a simple code-based structure to reason with. Functionality lives in implementation files, invariants are specified in test files. But if we think about this simple framework for quality assurance, we've only really looked at one of these two questions, the question of what our code actually does. And if we're talking about invariants, we can classify these again. We've got functional invariants, which are the things that specify how the code works, and structural invariants, which are how a thing fits into the world around it. And the tool that we have for describing functional invariants, those are our test frameworks, they're not actually good at describing structural invariants. We're very good at describing it where things will work, but we're not very good at describing the universe of places where things won't work. And for a very long time, the way that Python solved this was with documentation. On the other hand, types are really good at specifying structural invariants, and recent versions of Python can describe types for most reasonable Python code. So as well as providing structural invariants, you don't need to write as many tests because you can verify all the cases where a type doesn't work. If you can't specify the wrong type, you don't have to enumerate all the cases where a type error can happen. But I'm not here to evangelize types. I did that last year. I think types are great, but they still aren't universally popular. And there are really good reasons for that. Types are a tool for managing complexity, but it's not always clear when you've crossed the line of structural complexity that can't actually fit in your head. It's not even always clear when you begin writing a code base that your code base will achieve the level of structural complexity where typing will make sense. And genuinely, it can be really hard to judge when types are necessary. And once you do, you have to learn how to use an entirely new system, which can itself be quite complex. And so you end up with a trade-off. You could either have a simpler toolbox for managing your quality assurance, or you can have a simpler way to specify the structure of your code base. So you can have more tests and more documentation, or you can make your interfaces harder to read and harder to understand. So there actually isn't a correct answer here. Both approaches provide simplicity, and adopting either approach is going to leave some complexity somewhere else in your code base. So I'm going to finish off with a discussion of the evolution of Python, because a common complaint I hear is that Python is becoming more complex with every version, and it's worth taking some time to examine whether that is the case. Yes, of course Python is more complex than it used to be. Why is this even a question that we're asking at the moment? Python was, for a lot of us, a static language for quite some time. Python 2.7 was around for a very long time, and it was only around Python 3.5 that the language started becoming stable for people who needed Python 3 for things other than data science. And the language has been adding on features fairly regularly since then. That's all the things that have appeared in the last 8 or so years. And if you're used to Python not changing for 7 years, well, maybe you'd be asking yourself, well, what happened to simple is better than complex? To which I respond with print. Python has always been a language that has tried to model complexity for its users so that we can write simpler code. And one thing that happens as more people from more diverse communities use Python is that we discover more places where Python is not simple to use. And so now Python just models more complexity. Most of us decide to pick up only a subset of Python when we learned it. And likewise, as new features emerge, we only need a subset of those new features. As an API developer, I don't need matrix multiplication operator. But a data analyst probably won't need to define an async await in their Jupyter notebook. I gave a talk at Kiwi PyCon last year. I tried to make a point that a big part of Python's success is its willingness to support use cases from a diverse set of disciplines. And another talk by Grant here and Ben, they argue that you can very easily use a subset of Python's features and never need to think about the more complex ones until you need them. And they proposed a fairly workable model for that called the when of Python. So if I have some takeaway advice, is go to last year's Kiwi PyCon. And that's the secret here. It's this complexity is reasonably self-contained and it's optional until you need it. And this stands in contrast to needlessly complex languages like Java, or even necessarily complex languages like Rust. We want to model more things here. And so the question is, do you want a simple language or do you want your own code to be simple? So we're now at the end of the example section of the talk. I get to do some commentary because I like doing that. When we started this talk, we had this proposition that simple is better than complex. And we went through a bunch of examples that show when you're writing Python that someone is going to have to model complexity. In the world of Python, we're lucky that the language itself chooses to model a lot of complexity for us, and it provides us with tools that can model new and unexpected forms of complexity. But what I haven't spoken about is code that we write ourselves, which brings me to what I said at the top of the talk, is that complexity exists. It would be much better if it didn't, but our job here as programmers is to model complexity. It would be better if complexity didn't exist, but you can choose to contain complexity, or you can choose to not do that. And what I hope I've conveyed today is that we should be thinking about who should be experiencing simplicity and who should be experiencing complexity. And we tend to work in fairly narrow domains. Even if we're working in a team on the same project, different people will focus on different aspects of the code base. And with each of us tend to have a fairly good understanding of what we work on ourselves, and we have less understanding of things that other people have worked on. So it's probably best if we model our own domain's complexity so it's not complicated for other people, which is why you can end up with a giant pile of C code that does a lot of error handling for us, as well as printing things out, and you can call it print, which is the simplest interface, the literal first thing that people write in Python. Thank you. And that's the point. Our code has end users, be it consumers or even other software developers on our same team. Code tends to be part of a bigger system. It exists because we're modeling some sort of complexity better than a human could. Your code has dependencies. Each one of these dependencies, from the Python interpreter to the packages your dependencies depend on, they all model some complexity so that you don't have to. Otherwise, it wouldn't be useful to you. And your code might be somebody else's dependency. And what we've seen earlier in this talk is that things that are the simplest thing now can change as we get newer tooling or as people's opinions about what things are good change. And we've seen that what's simplest may depend on a trade-off between more upfront work and deferring decisions until later. For me, a guiding principle is that simplicity can be a gift that you give to other people. If simple is better than complex, then leaving your end user with a simpler experiencing and managing your own complexity in your own code is better. And also, I lied, I'm going to evangelize types. Types at your interface give your users less complexity to need to worry about, simply because you've told them what things won't work with your code. So if you want to do a really easy thing to model complexity for your end users, annotate the interfaces that you export to other people. And more generally, simplify things appropriately, because I think that what you should take away from this talk is that simple interfaces are a thing that we should strive for and complex ones are not. Simplify in the wrong place and you remove so much complexity as to be useless and inactionable, and you get talks like this one. Bah.
So much, Chris. We do have time for a couple of questions if anybody would like to ask them. One up back, Jordan.
Thank you so much for the talk. I want to ask, does your opinion change if it's working on a project where you are the only developer versus a team? Or does that complexity trade-off still feel about the same when you're working with multiple devs?
So two things. One, if I know the code is going to be throwaway and I'm not going to use it in another year, which is always a wrong assumption, I will normally write the smallest amount of code that I can do. But generally speaking, me in a year's time is a new developer. So yeah, all my advice is the same to myself for a year from now. Anyone else?
That looks like a no.
Oh, there's one up the back.
There's one at the back. Okay.
How do you respond to the idea, the suggestion that the idea of the game is to get as many people, humans, between you and the metal?
What?
I think
that was the answer to the question.
All right. No more questions?
Thank you.
Thank you so much, Chris.
Thank
We
you,
have-
Chris.